Okay. So the things we have covered so far is what is a linear and circularly polarized light. This is one of the topic we have covered so far. Secondly, we have covered what is circular birefringence, which is in other term we also known as optical rotation. So again, circular birefringence is the effect where the refractive index of the two different circularly polarized light, the left hand and right hand, are different, and the effect is that we will see an optical rotation. Third one is circular dichroism. And the effect of that is ellipticity. And then the fourth one we have covered is what is the molecular picture or the molecular reason for optical activity, or in this term we are saying CD, the circular dichroism, why the molecule absorb both of them differently. And the fifth one, how to represent this optical rotation and ellipticity. So we come to know the optical rotation dispersion, or ORD, and CD spectroscopy. So we'll come into that question when this plane curve region comes in ORD one more time. But before going there, these are the 5 important parts that you need to understand from the portion we have covered so far. So I'll go through that, but any other question up to this part before you go further, other than Ghazal's question that I will answer?
Sir, this is Somnath here.
Yes, Somnath.
I wanted to know that if we can see the due to difference absorption, we see the ellipticity, but in case of optical rotation, we see that difference in velocity in velocity of light. So how they are related to each other?
Okay, so very good question. So we'll cover it one by one. So both of your questions are actually somehow connected to each other. So let me go into that. So first, the answer for Gajal's question. Okay, so let me stop sharing for a minute, and then I'll share that one more time. Can you all see my screen? Yes. Okay. So the question is why? First, answer me Somnath's question, because that will lead to Ghazal's question afterward. So first, why we actually see the circular dichroism or ellipticity effect, and when we see the circular birefringes or optical rotation effect. Now, what we already know that when a circularly polarized light is actually going through a sample, so one is say like the right hand rotation light, and say the other one is the left hand circularly polarized light. So they are going through, and they are going through the sample. Okay, and the sample itself has a asymmetric electronic distribution. And this is going to interact both this RCP and both this LCP differently. Now, how it is interacting, that depends on the molecule itself. Now, there are two possibilities. First possibility is, first possibility is that the molecule is interacting only through the absorbance. Okay. That means it is absorbing one of them, either the RCP or LCP more compared to the other. Sorry, there is some technical glitch. So they're absorbing one of them more than the other. So this AL is not equal to AR, where the AL represents the absorbance in the left-hand circular polarized light, and AR represents the right-hand circular polarized light. So now what happens?
Sorry, sir, there's a lot of background music.
Yeah, so it is probably actually not from my side. So if everybody please can mute yourself, that would be really great. And if you have any question, then you can unmute yourself and answer. Okay, now it's much better. So the thing is that okay. So the reason is that over here, what happens that one of them is actually absorbed. Okay. Why it is absorbing? Because the wavelength of this right hand or left hand circular polarized light is a region where actually there is an absorbance for the molecule itself. And that's why it can differentiate both this left hand and right hand circular polarized light. And depending on the actual electronic distribution of the molecule, it is absorbing one of them more than the other. So that's why I'm seeing this different. AL and AR are not same. And depending on that actual structure of the molecule, actual orientation of the electronic structure, which one of them will be absorbed more, depending on that, I will get an ellipticity psi, and its signature will depend on which one of them is actually getting absorbed more. If the left-hand circularized polarized light, that means AL, is absorbed more than the AR, I'm going to get a positive number. And for the enantiomer of the same molecule, I'll get the opposite one. Now what happens as a second interaction? Second interaction is depending on the refractive index. And this refractive index is such that one of them is different than the other. NL and NR are different. Now the question is, why this NL and NR are different? What is refractive index? Refractive index is nothing but a ratio of how fast the light is going with respect to how fast the light actually moves through vacuum. So when there is a medium you have, that means you have some molecule, some electronic density. So that is actually interacting with the light, which is nothing but itself electromagnetic radiation. So when they're interacting, and if the light that you're giving has a helicity, that means either right hand or left hand polarized light, and your molecule itself has an optical activity where itself it can create an helicity. We have discussed that why. And then what can happen? It can detect this left hand and right hand polarized light differently. So one of them will interact more than the other. So which of them is actually interacting more, that will slow down, and the other one not interacting, it will pass by very fast. Okay, so that's why over there we're not seeing any absorbance, because it is not a region where it is actually absorbing, but itself it can still interact with the light passing by. And why it is? So let me give you the answer through some equations. So now if we discuss that what is refractive index, I don't know what is happening. A refractive index is given by the velocity of light in vacuum and the velocity of light in the medium. And this particular function, when it is actually happening, it also depends on the wavelength of the molecule. Why? Because when we can say the velocity of light in a medium, it can be given as a function of lambda and nu. Lambda is the wavelength and nu is the frequency of the light. And I'm quite sure you guys already know what is a wavelength and what is a frequency. So what is wavelength? Wavelength is that if there is a wave like that going through, what is the difference between the same phase, like same phase just next to each other? I mean the corresponding same phase, what is the difference between these two? That will be given as lambda. Okay, and you can take that at any particular point, but at the similar phase, either take peak to peak or trough to trough or middle to middle, whatever you take, that should be the same distance. Okay, and that is what is known as wavelength. And what is frequency? At unit time, how many such repetition you are seeing. Okay, and that is going to give you the frequency of the light. Now, when a light passes through a system, I am seeing that velocity is getting changed. Now, this too is a constant, and this velocity is changing. So some of them actually have to change. And what is actually getting changed is the wavelength. Okay, so when the light passes through a medium and it is changing its velocity, it is the wavelength that is actually changed. The frequency remains the same. Okay, so that's why what happens, the velocity that you are changing, that means with respect to the interaction with the molecule, it is going to affect the velocity, but at the same time, it is also going to change its wavelength. And that's why the refractive index, it is very much dependent on the wavelength. So whenever we talk about a refractive index of a molecule, we generally talk about what is the wavelength where we are measuring the refractive index. And similarly, when we are talking about a change in the refractive index, that means optical rotation, over there we also have to mention what is the wavelength I'm talking about. Because depending on the wavelength, the velocity changes and the refractive index also changes. And that's why when a molecule actually interacting with a passing light, depending on the interaction, it can be at particular wavelength. Either it can be absorbing, that means a circular dichroism. But when it is only passing through the system, it depends on the interaction between the electronic field and the passing light electronic wave. And that depends totally on the molecular interaction or the molecular structure. And that's why sometimes you can have an effect on the refractive index where it is not even absorbing. And one of the example of that we discussed last class is actually the sucrose solution. So what we generally expect in a molecule, that when we are measuring that optical rotation of a molecule, what do we expect? That it is going to show a curve like this. Okay, and then its enantiomer should show me a curve like this, and it should match and go to 0 at a wavelength where actually it is not absorbing at all. Okay, when it's absorbing 0, the value of optical rotation should be 0. But depending on the molecular structure, somewhere it can still interact with the light, although it is not absorbing, but it still can affect its movement. And that's why it can still show the difference between the refractive index for the left hand and right hand polarized light. And as a result, what happens, this molecule can show something like this. And similarly, the other enantiomer will show something like this. So over here, what you are seeing, that is a very important part over here. Here you are seeing the absorbance is 0, but the phi is actually not 0. It is a non-zero value. Why? Because over here, the light, the molecule still differentiating between the movement of the molecule. Okay, and this particular region of that molecule, the ORD spectra, optical rotated dispersion spectra, is known as the plane curve. Okay, because it is only depending on the movement of the light. There is nothing absorbance associated to that because the molecule doesn't absorb at all. And as I was saying yesterday, the sucrose solution, when we did the test of optical rotation, we did that at 590 nanometer in a visible region, a yellow visible region. Whereas the sucrose solution, when you make a sucrose solution, it is actually colorless. That means it doesn't even absorb in the visible region. Why it is still showing an optical rotation, but it is not even absorbing? That is because of this particular plane curve region, because it is still interacting with the light, although it is not absorbing. Okay. So I hope Somnath and Ghazal, I have answered your question, or you still have some doubt. Please let me know.
Yes, sir. Done.
Okay. Any more question, anyone? Okay, nothing more. So now today we are going to